Still on the stochastic processes playlist and considering Poisson processes in particular. This is the fifth video on Poisson processes, and after this, there'll be one more, and then we'll move to some other things on the stochastic processes playlist. So here we're looking at compound Poisson processes, compound Poisson processes. Straight off, a compound Poisson process models situations where events occur randomly over time, and then each event has a random size, or what you can call a magnitude. And you have examples such as insurance claims, like number of claims plus the size of the claims. These things don't happen. Insurance claims don't happen that regularly, right? They are chance events. Then you have financial transactions, you have queuing systems, and all of that. By definition, let n of t, the number of arrivals or whatever it is you're considering, follow Poisson distribution with parameter lambda t, and that is the number of events up to time t. And then we have the collection of all xi's to be independent, to be IID, random variable event size. I've forgotten what IID is. I know independent distribution. Uh, I've forgotten okay, maybe I can quickly check that up. It's a very common term in statistics. I know independent distribution is IID, independent and identically distributed random variable. Yeah, independent and identically distributed. Yeah, that's the deal. So independent and identically distributed, that's what XI is. Talking about the event sizes, then N of T is independent of XI. That is N of T, the number of event does not depend on the random variables, talking about the event sizes. Then we say the compound Poisson process is S of t equals summation from I equals 1 to n of t of xi, with the convention that S of t is 0 if n of t is equal to 0. So the interpretation of this is that n of t is the number of events, xi is the size of each event, and S of t is the total accumulated value of the event. So we are summing a random number of random variables, basically. The mean, for the mean, right? We have the mean to be the expected value of S of t, which is the expected value of nt multiplied by the expected value of x. So the expected value of n of t is usually known to be lambda t for a Poisson distribution. And we get that the expected value of S of t is lambda t mu. Lambda t mu is the mu for a compound Poisson process. And then we go for the variance. So variance of S of t is the expected value n of t multiplied by variance of x plus variance of n of t multiplied by the expected value of x all squared. So variance of n of t, we know that to be lambda t, and we get that variance of s of t is lambda t sigma squared plus lambda t mu squared. And then variance of s of t altogether would be lambda t into sigma squared plus mu squared. So that's lambda t plus standard deviation squared plus mu squared. So moment generating function, which if I have a whole playlist on that actually, so that's m sub s of t of s equals exponent of lambda of t into mx of s minus 1. That's the moment generating function for a compound Poisson process. So, and then we have special case, you have a special case where xi is equal to 1, right? So if all jumps are 1, then we say that s of t is equal to n of t. So we say the compound Poisson process reduces to a standard Poisson process in that case when xi is equal to 1. So we have an example here. Given that lambda is 2 times 3, xi is exponentially distributed with parameter 1, then we know that the expected value of x here is 1. The variance of x is also 1. Knowing that, yeah, we know that that's 1 apiece. So the mean of the mean of the mean is given as expected value of S3. That's S at time 3. That will be 2 times 3 times 1, based on the fact that we have 2 times 3 times 1 like this. So this is 2, 3, and then 1, making 6. Then the variance will be 2 times 3 times 1 plus 1, which gives 12 in this case. So we can then do that using Python code. Um, so we simulate a compound Poisson. Um, for everything inside the range of n sim. So okay, we have a function defined simulates compound Poisson. We have parameter t, lambda, size of the distribution, and n sim, that's 1. So we put all of that together. We have lam Poisson distribution of lambda t, and by the time it's all done, of course, t is 2, lambda is 2. By the time it's all done, we have the sample mean to be about 6.01 and all that, and sample variance is like 12.2. Then we have this compound Poisson distribution. Of course, as you keep running, it keeps changing because we're talking about a stochastic process, which is a system, a, a system that evolves over time randomly, like that. Then we talk about path representation. So let Ti be arrival times. Ti are the arrival times. Then we say that S of t is summation from I equals 1 to infinity of xi multiplied by 1. Then for Ti less than or equal to t. So in this case now, if you put it all together, if you use simulate that in Python, right? So you define simulate path from time 0, s0, and then you go over time, and then if you run that, get you get this compound Poisson sample path. Of course, as you keep running, it keeps changing to 16 now. This is 20.0, and all that. Then we then have key properties. So key properties for compound Poisson process. So for disjoint intervals, we know that S of T2 minus S of T1 is independent of S of T4 minus S of T3. So, and you have stationary increments. So the same thing applies, right? S of T plus H minus S of T is approximately S of H. Then you have the jump process where we have piecewise constant. Then you have jumps occurring at random times. And you have the advanced example of for thinning. If you suppose that lambda is 5 and xi uh, follows Bernoulli distribution probability 0.3, then we say that S of t follows Poisson with first of all, we have lambda t, right? 5 times t, then with that probability 0.3. So this is called Poisson thinning, like that, because probability is now involved in that process. Then we can apply the regular Poisson formula. So in summary, for compound Poisson process, we then know that a compound Poisson process is S of t equals summation from I equals 1 to n of t of xi. And we have key result that the mean is lambda t mu. Variance is lambda t, sigma squared plus mu squared, and then the jump process with independent increments is also there. So it models systems with random arrivals and random magnitudes. So we have practice problems as usual. Um, let n of t follow Poisson 3t and xi follows exponential 2. Then we need to find es of 1. All right. So um, so it follows the kind of thing we've done here before. So if you have for ES of 3, right, you just follow this kind of thing. ES of 1, that is lambda t times this value here, that exponential. Lambda t times that exponential thing. So lambda t, so that'll be so lambda t, that's 3t already times 2. That should be 60 basically. Then you have all of that going. So for the variance too, so use formula for variance. I think we have something sigma squared plus t squared. Yeah, lambda t into sigma squared plus mu squared. Okay, s of t. So we can have that also. Then we have same thing going on here. Exponent, expected value of S5, you know. So just multiply. Okay, yeah, expected value of X is already 3 here. So we put all of that together to get this. So you want to try your hands in all this and see how well it goes. So just apply the formulas as you have them, and let's see how clear it is. So if you can let me know your answer in the comments, either on YouTube or on Facebook. And of course, if you have issues solving any of the problems, you can let me know. So I might just be able to solve like one or two of them in separate videos like this. So try your hands on all of this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Um, If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right now? Hit the notification bell so you can always get alerted each time a new video is released. You can also click on join to become a member of the channel, and that gives you special privileges like getting to see some videos first or getting to see some videos exclusively because you're a member of the channel. We can also hang out. You can request for PDF copies of my notes. We can hang out to discuss whatever interests you on my channel, be it maths, be it data analytics, data science, and scholarships, machine learning, anything like that. So let me know which one interests you. So try your hands on the problems. So questions 1 to 4 here. Then this is 5 to 9. Then 10 to 14. Then 15 to 15. So this is 15 to 19, right? Then I can have 16 to 20 showing. So try your hands on all of this. Let's see how well this goes for you. Then follow the examples to do all of this. Okay, so till I come your way again, keep doing maths right. Bye. So after this, I have one more video for Poisson process, and then we'll move on to I think st continuous Markov chains or so, something like that. I'm not sure which one. We still have Q theory ahead. We still have martingale and all of those things ahead. So we are on a ride. Let's keep going. See you.